Hey everybody, today we will be proving some stuff about the ordinary least squares estimator, which tries to estimate a parameter using the data and the outputs generated by that data. So the first thing we want to show is that beta hat is linear with respect to y. And so we know beta hat equals this, and then if we just let the coefficients be a matrix, we have that this then equals ay, which is linear. Next, we want to show that our distribution follows the following normal distribution. So, given our y is a linear transform of x with some parameter epsilon that has epsilon normally distributed around mean zero and variance matrix sigma squared times the identity, our least squares estimator will be distributed like this. So first we want to show the mean. And that's the expectation of beta hat, and that is the same as the expectation of whatever beta hat is. And since we know that beta hat is linear in y, we can just take out our coefficients. And since we know that y is a function of x, we can just replace that back in too. So x transpose x inverse x transpose times the expectation of x beta plus epsilon. And since we know the expectation of epsilon equals 0 because it's normal 0 sigma squared by identity, we actually have this whole thing equals x transpose x inverse x transpose x beta. So now here we have some matrix, let's just say A inverse by A by beta. Well, this will always cancel, so this whole thing just equals beta. So our mean of our ordinary least squares estimator is just beta. Now, our variance, we have the variance of beta hat equals the variance of whatever beta hat's represented as x transpose x inverse x transpose y. And so there's actually a formula for that. So the variance of ax, where a is a coefficient and x is a random variable of a matrix, is actually a inverse variance of x. No. It's a by the variance of x by A transpose. And so we'll just have to use that right here, and we'll say that we have x transpose x inverse x transpose times the variance of y times x times x transpose x inverse, right? So if we have transpose of AB, that equals B transpose A transpose. So that's the same thing I was doing here. I have X transpose, I transpose it first, X, and then I keep the inverse, go on whatever's the other side, and then I transpose on the inside, but both are X, so it's just still X transpose X. And so what is the variance of Y? Well, the variance of Y is just the variance of actually epsilon because we have our random variable, we have our x that is just our data, and the randomness is only coming from this epsilon. So whatever the variance of y is, and beta is just some mean parameter that we're trying to estimate. The variance of y is just the variance of epsilon, which is actually just our variance times our identity. So right, because remember x is just some data and y is some kind of output, kind of binary classification case. So given that, now we have that our entire expression is just x transpose x inverse times sigma squared identity times x by x transpose x inverse. And so now this whole thing is just sigma squared, because it's a constant x transpose x inverse. Oh, there's a lot of x's, so there's another x transpose here. Don't, it's not x transpose x inverse times whatever. No, it's x transpose x inverse times another x transpose. So yeah, x transpose, well, anything times the identity is just anything, so I don't really need to keep the identity here, times x times x transpose x inverse. So same thing, A inverse times A, we just cross this whole part out, so this just equals sigma squared x transpose x inverse, and that actually is the same as what we had here. So now we've computed the mean and the variance, so we know that our ordinary least squares estimator is distributed as is normally distributed with mean beta and variance sigma squared times a positive semi-definite of our data. And that just proves both linearity and the distribution of our ordinary least squares estimator. Thank you.